Welcome! In this session, we'll dive into LeetCode problem number 1984, titled Minimum Difference Between Highest and Lowest of K-Scores. This is a fascinating problem that challenges us to find a subset of scores with the smallest possible range between the highest and lowest values. Let's explore how we can solve this step by step. In this problem, you're given a zero-indexed array called nums, where each element represents the score of a student. Along with this, you're also given an integer k. Your goal is to select exactly k scores from this array in such a way that the difference between the highest score and the lowest score among the selected k scores is as small as possible. The task is to return this minimum possible difference. To break it down further, the input includes the array nums, which can contain up to 100,000 integers, each ranging from 0 to 1 million. The value of k will always be at least 2 and at most equal to the length of the array. The output will be a single integer representing this minimized difference. To help you better understand the problem, here are some examples. In the first example, the input array is 90 and k is 1. Since there's only one score to choose from, the highest and lowest values are the same, resulting in a difference of 0. In the second example, the array is 9, 4, 1, 7, and k is 2. By selecting the scores 4 and 7, the difference between the highest and lowest scores is 7 minus 4, which equals 3. This is the smallest possible difference when choosing any two scores. Finally, in the third example, with the array 1, 5, 8, 10, and k equal to 3, you can choose the scores 5, 8, and 10. The difference between the highest score, 10, and the lowest score, 8, is 2, which is the minimum difference for this case. Now, let's consider the constraints and some additional points. The array nums can have a length between 1 and 100,000, and each score in the array falls within the range of 0 to 1 million. The value of k is always at least 2 and at most equal to the length of the array. It's also important to note that the array may contain duplicate values. Given the large size of the input, the solution needs to be efficient. One effective approach to solving this problem involves sorting the input array. Sorting helps us quickly identify the optimal range of k scores with the smallest difference, significantly reducing computational overhead and making the solution scalable for large inputs. In this problem, we are tasked with selecting k scores from an array nums such that the difference between the highest and lowest scores in the selected subset is minimized. To achieve this, we need an approach that efficiently determines this minimum difference. One possible method is the brute force approach, where we generate all possible combinations of k scores from the array. For each combination, we calculate the difference between the maximum and minimum values and track the smallest difference encountered. While this method is intuitive and easy to implement, it has significant drawbacks. Specifically, the time complexity of generating combinations grows exponentially with the size of the array, making it impractical for larger inputs. For example, using a library like itertools.combinations in Python highlights how quickly this approach becomes computationally expensive. As a result, while the brute force method works for small cases, it is not scalable or efficient for solving this problem on larger datasets. An alternative and much more efficient solution is the optimized approach, which uses sorting and a sliding window technique. The intuition here is that, once the array is sorted, the smallest difference between the highest and lowest scores in any subset of k scores will be found within a sliding window of size k. By sorting the array, we ensure that all potential subsets of size k are adjacent, which simplifies the process of finding the minimum difference. After sorting, we iterate through the array using a sliding window, calculating the difference between the first and last elements in the window. This allows us to track the smallest difference encountered without the need to generate explicit subsets. The time complexity of this approach is dominated by the sorting step, which is O, n log n, followed by the O, n, traversal of the array using the sliding window. Together, this gives an overall complexity of O, n log n. This method is efficient and well-suited for larger inputs, though it does involve sorting the array, which may add overhead if the input is already sorted or nearly sorted. Given the constraints and requirements of the problem, the optimized approach using sorting and a sliding window is the clear choice for solving this problem. This method achieves an efficient O, n log n, time complexity and is scalable for larger arrays. By leveraging sorting, we ensure that subsets of size k with the smallest differences are adjacent in the array, and the sliding window eliminates the need to explicitly generate all subsets. This saves both time and space. Although sorting introduces a pre-processing step, the overall efficiency far outweighs this minor trade-off, particularly when compared to the brute force method, which becomes infeasible for large inputs. This approach is not only optimal for this specific problem but is also a widely applicable technique for similar problems involving subarrays and ordered conditions. By combining clarity and performance, the optimized approach strikes the right balance, providing an elegant and scalable solution to the problem. To tackle this problem, we aim to minimize the difference between the highest and lowest scores in a group of k elements selected from the array nums. This can be visualized as finding the minimum range of a sliding window of size k over a sorted version of the array. The first step is to sort the array. Sorting is crucial because it allows us to focus on consecutive elements within the array, which minimizes the range naturally. Sorting ensures that any potential group of k elements that aren't adjacent would have a larger range, making them unnecessary to consider. For example, if the array is 4, 2, 1, 7, sorting it gives 1, 2, 4, 7. Next, we initialize a variable min_diff to a very large value, such as float, inf. This variable will help us track the smallest range found during our iteration. Then, we iterate over the sorted array using a sliding window of size k. For each window, we calculate the difference between the maximum and minimum values, which is simply the difference between the last and first elements in the window. If this difference is smaller than the current min_diff, we update min_diff. This approach ensures that we systematically evaluate all possible groups of k consecutive elements to find the smallest range. For example, let's consider nums equals 1, 2, 4, 7, and k equals 2. The sliding windows here are groups of 2 consecutive elements. In the first window, 1, 2, the difference is 2, 1 equals 1. The second window, 2, 4, has a difference of 4, 2 equals 2. In the third window, 4, 7, the difference is 7, 4 equals 3. Among these, the smallest difference is 1. At the end of this process, we return the value of min_diff, which holds the smallest range found across all windows. The key insight is that sorting simplifies the problem by allowing us to focus solely on consecutive elements in the array. This eliminates the need to consider all possible combinations of k elements, which would be computationally expensive. The sliding window technique further optimizes the process by ensuring that we calculate the range for each window in constant time. This approach is effectively greedy because we always evaluate the smallest range in the current window, guaranteeing an optimal solution without backtracking. Together, sorting and the sliding window method ensure an efficient solution with a time complexity of n log n. The algorithm relies on simple yet effective data structures. The main data structure is the sorted array nums, which ensures that the sliding window approach works as intended. Additionally, we use variables like min_diff to store the smallest difference found in window_diff to calculate the range of the current window. In terms of complexity, the sorting step dominates the time complexity at n log n. Once the array is sorted, iterating over it with a sliding window takes linear time, n. Therefore, the overall time complexity of the algorithm is n log n. For space complexity, since the sorting operation can be performed in place using algorithms like timsort, the space complexity is 1. This makes the algorithm both time-efficient and space-efficient, suitable for handling large input sizes. Certain edge cases are important to consider when implementing this solution. First, if the size of the array, len, nums, is less than k, the problem is invalid because it's not possible to select k elements. Depending on the requirements, you can return 0 or handle this scenario appropriately. Second, if all elements in the array are the same, the difference between the highest and lowest values in any group will always be 0, regardless of the value of k. Similarly, if k equals 1, the range is always 0 since a single element has no variation. Finally, when k equals the size of the array, the range is simply the difference between the maximum and minimum values of the entire array. These edge cases ensure that the algorithm handles all possible inputs robustly. Now, let's walk through an example to see the algorithm in action. Take the input nums equals 9, 4, 1, 7, and k equals 2. First, we sort the array, resulting in nums equals 1, 4, 7, 9. We then initialize min_diff to a very large value, such as float, inf. Next, we calculate the range for each sliding window of size k. For the first window, 1, 4, the difference is 4, 1 equals 3. The second window, 4, 7, also has a difference of 7, 4 equals 3. The third window, 7, 9, has a smaller difference of 9, 7 equals 2. Among these, the smallest difference is 2. We update min_diff to this value and return it as the final result. This example demonstrates how the algorithm efficiently finds the minimum difference by focusing on consecutive elements in the sorted array. The result, 2, represents the smallest range achievable for any group of k equals 2 elements in the input array. This solution for LeetCode problem number 1984, minimum difference between highest and lowest of k scores, efficiently calculates the minimum difference between the highest and lowest scores in any group of k scores. The function minimum difference starts by handling the edge case where k equals 1. In this case, the minimum difference is always 0 because a group of 1 score has no range. Then, the input list nums is sorted in ascending order. Sorting ensures that the smallest possible difference between the highest and lowest scores in a group of size k will always occur within a contiguous subarray. Next, we initialize min_diff to infinity. This variable will store the smallest difference we find as we iterate through the array. Using a sliding window approach, we calculate the difference between the highest and lowest scores for each window of size k. Specifically, for each starting index I in the range 0 to len, nums, k, the highest score in the window is nums, I plus k1, and the lowest score is nums, I. The difference is calculated as nums, I plus k1, nums, I, and we update min_diff if this difference is smaller than the current value of min_diff. Finally, after iterating through all possible windows, the function returns min_diff, which represents the minimum difference between the highest and lowest scores in any group of k scores. The algorithm has a time complexity of O, n log n, due to the sorting step, and the sliding window iteration runs in O, n, making it efficient for large inputs. This is the Java implementation of LeetCode problem number 1984, minimum difference between highest and lowest of k scores. The logic mirrors the provided Python solution. The input array is sorted, and the minimum difference is computed by iterating over the sorted subarrays of size k. Key differences include explicit type declarations in Java, the use of arrays.sort for sorting, and managing integer-specific operations like integer.max_value. To solve this problem, we need to find the smallest difference between the highest and lowest scores in any subset of size k from an array of scores, nums. The most efficient way to do this is by sorting the array first. Sorting ensures that the elements in any subset of size k are contiguous, which simplifies the process of finding the smallest range. Once sorted, we use a sliding window approach to iterate through all possible subsets of size k. For instance, consider the example nums equals 90, 100, 78, 89, 67, and k equals 3. First, we sort the array, giving us nums equals 67, 78, 89, 90, 100. Then, we initialize min_diff to a very large value, float, inf, to track the smallest difference as we iterate through the array. The sliding window will examine each group of k elements, starting with the first three, 67, 78, 89. For the first window, 67, 78, 89, the difference between the highest and lowest values is 89, 67 equals 22. We update min_diff to the smaller of float, inf, and 22, so min_diff becomes 22. Next, we slide the window one position to 78, 89, 90. Here, the difference is 90, 78 equals 12, so min_diff is updated to 12. Finally, for the window, 89, 90, 100, the difference is 189 equals 11. Since 11 is smaller than the current min_diff, we update min_diff to 11. At the end of this process, the smallest difference among all subsets of size k equals 3 is 11, so the output is 11. Now let's look at another example where nums equals 1, 3, 6, and k equals 2. Here, we start by sorting the array, which results in nums equals 1, 3, 6. As before, we initialize min_diff to float, inf. The first window is 1, 3, where the difference is 3, 1 equals 2. We update min_diff to the smaller of float, inf, and 2, so min_diff becomes 2. The next window is 3, 6, where the difference is 6, 3 equals 3. This time, 3 is larger than the current min_diff, so min_diff remains 2. After examining all possible subsets of size k equals 2, the smallest difference is 2, and the output is 2. Now let's consider a larger example with nums equals 10, 20, 30, 40, 50, and k equals 4. In this case, sorting the array gives us nums equals 10, 20, 30, 40, 50. We initialize min_diff to float, inf, and start evaluating subsets of size k equals 4. The first window, 10, 20, 30, 40, has a difference of 40, 10 equals 30. We update min_diff to 30. The next window, 20, 30, 40, 50, also has a difference of 50, 20 equals 30. Since the difference remains the same, min_diff stays at 30. After evaluating all subsets, the smallest difference for this example is 30, and the output is 30. Let's summarize the key insights from this approach. Sorting the array is a crucial step because it ensures that subsets of size k are contiguous, allowing us to use a sliding window to efficiently calculate differences. By iterating through the array, we systematically evaluate all possible subsets of size k and track the smallest difference. This approach is efficient, with a time complexity of O(n) log n for sorting the array and O(n) for the sliding window traversal, making it suitable for large input sizes. The combination of sorting and the sliding window ensures both simplicity and optimal performance for this problem. Here, we analyze the time complexity of our solution. The first major operation is sorting the input array. Sorting, as you might know, takes O(n*log n time, where n is the size of the input list. This step is necessary to ensure we can efficiently evaluate the differences between elements in sorted order. Once the array is sorted, we use a sliding window approach to find the minimum difference. This involves looping through the array, where the loop runs approximately nk plus 1 times. Within each iteration, we calculate the difference between the highest and lowest values in the current window, which is a constant time operation, or O(1). When we combine the sorting step with the sliding window iteration, the sorting process dominates because O(n*log n grows faster than O(n). Therefore, the overall time complexity of this solution is O(n*log n). Now, let's examine the space complexity of the solution. The first factor is the space required to store the input array itself, which is O(n). Sorting the array may also use additional memory, depending on the algorithm. Python's built-in timsort, for example, is an in-place sorting algorithm, but in the worst case, it can use up to O(n) additional space. Besides sorting, we only use a few auxiliary variables such as min_diff and diff, which take constant space, or O(1). Since the dominating factor in space usage is the input array and potentially the sorting operation, the overall space complexity of the solution is O(n). Now let's compare our optimized approach to a brute force method. In a naive solution, we would generate all possible subsets of size k from the array, compute the maximum and minimum for each subset, and then find the minimum difference across all subsets. However, the number of subsets of size k is given by the combination formula C, n, k, which can grow exponentially as O(n) to the power of k, in the worst case. Additionally, for each subset, calculating the max and min values would take k time. This results in a total time complexity of O(n) to the power of k*k, making it computationally infeasible for larger inputs. In contrast, the optimized approach sorts the array and uses a sliding window, requiring only O(n*log n time. This is drastically more efficient, highlighting the advantage of the optimized solution over brute force. Finally, let's consider the best, average, and worst case scenarios for this solution. In the best case, the input array is already sorted. Even so, the sorting step still takes O(n*log n, and the sliding window operation adds O(n). This results in an overall time complexity of O(n*log n). In the average case, where the array is unsorted, the sorting step dominates as O(n*log n, and the sliding window operation remains O(n). Once again, the total time complexity is O(n*log n). Similarly, in the worst case, where the array is completely unsorted, the sorting operation still dictates the overall time complexity at O(n*log n). To mathematically confirm the big O, we observe that O, n asterisk log n, grows faster than O, n, so the sliding window's contribution becomes negligible for large n. Thus, the time complexity remains O, n asterisk log n, and the space complexity remains O, n, due to input storage and auxiliary memory requirements. One of the most common mistakes in this problem is neglecting to sort the array before attempting to solve it. Sorting is absolutely essential because the greedy approach, which selects k consecutive elements to minimize the range, depends on the array being ordered. Without sorting, you cannot ensure that the chosen elements represent the smallest possible range. Another frequent pitfall is using a brute force approach, which involves evaluating all possible subsets of size k. This method has a time complexity of O, n to the power of k, making it computationally unfeasible for larger inputs, such as arrays with tens of thousands of elements. Additionally, errors are often introduced when implementing the sliding window technique. Mismanaging the bounds or failing to update the window properly can lead to off-by-one errors or skipped elements, which ultimately compromise the solution's correctness. Lastly, always validate that k is a valid input. For instance, if k is greater than the size of the array, or if other constraints are violated, the program should handle these cases gracefully instead of assuming k is always valid. Another common point of confusion is equating this problem with subarray problems. While many problems involve contiguous subarrays, this one does not. It focuses on selecting k elements, regardless of their positions in the array. This distinction is important to avoid incorrect assumptions about the solution. Now, one of the key insights for solving this problem efficiently is recognizing that sorting the array simplifies the process. Once sorted, the smallest range for any k elements will always occur within a consecutive subsequence of the array. This insight allows us to adopt an O, n log n approach, combining sorting with an efficient sliding window technique. Recognizing patterns like this is invaluable, as many problems involving minimizing ranges or maximizing differences rely on similar strategies. During interviews, it's also important to discuss edge cases, such as arrays with fewer than k elements, arrays where all values are identical, or scenarios where k equals 1, which is a trivial case with a range of 0. Highlighting how sorting reduces complexity and explaining why brute force is impractical can set you apart as a candidate. If you're looking to deepen your understanding of this problem, consider exploring related problems that share similar patterns. For example, LeetCode 295, Find Median from DataStream, involves efficiently finding the median, a task that often requires sorting or maintaining order dynamically. LeetCode 1208, Get equal substrings within budget, is another sliding window problem that focuses on minimizing or maximizing a range under certain constraints. Similarly, LeetCode 1838, Frequency of the most frequent element, involves adjusting values to maximize frequency, which also employs sliding window techniques and range adjustments. Finally, LeetCode 209, Minimum Size Subarray Sum, is another classic sliding window problem but with a focus on subarrays. By studying these problems, you'll not only reinforce your understanding of sliding window techniques but also recognize how these concepts reappear across different scenarios. When considering alternative approaches, it's helpful to understand their trade-offs. One option is brute force, where you evaluate all possible subsets of size k and calculate the range for each. While this method is conceptually straightforward, its O, n to the power of k, complexity makes it impractical for larger input sizes. A much more efficient approach combines sorting with a sliding window. Sorting the array has a time complexity of O, n log n, and then evaluating the range of every subsequence of length k can be done in O, n. This method is both efficient and relatively simple to implement, which makes it the preferred solution. Another alternative is a heap-based approach, where you dynamically maintain the smallest and largest values. This method can achieve a time complexity of O, n log k, but is more complex to implement and may only be advantageous under specific constraints. By mastering the sorting and sliding window method while being aware of other approaches, you can demonstrate a balanced understanding of efficiency and flexibility during interviews. Thank you for joining me in solving problem number 1984. We've learned how sorting and sliding window techniques can help minimize the difference in a subset of scores. Remember, practicing similar problems will strengthen your algorithmic thinking. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!